So, isomorphism theorem. As I mentioned, this is the main theorem of the paper and therefore of this entire workshop. And there are two versions. There is a module version that is stated in the paper, but for that module, to state that module version, I need to introduce a few more silly things. There are some silly things that we consider, right? The fact that you look at rationals rather than reals, etc. These are some minor, as Vishwanath was saying, these are not very deep. Nevertheless, they are useful in they are useful conventions. Okay, so similarly, there are in order to state the module version, I have to introduce an algebra. He introduced an algebra, and then states it in terms of that module for that algebra. Okay, it's no big deal. Okay, here is another version, which is the graph, colored, directed graph isomorphism. That is the version we are stating. That module version and this are just the same, except, I mean, they are not, to go from one to the other does not involve any deep thinking. It's just a change of language, that's all. So what is this? So I choose my path in P plus and or maybe pi prime also, pi and pi prime in P plus, and look at B pi, right? What is this? This is the colored, okay. So let's write out the conventions here. Once again, what is P plus? Can someone please say? All paths which lie and endpoint is an integral weight. Okay. So this is image. So I'll write it. Endpoint is integral weight. And image lies in dominant while chamber. Okay, I take two such paths, and what is B pi? Right, right, very good. So this is the set of paths. Let me use a slightly different language today. Set of paths, let's say, generated by using root operators from pi. Okay. Of course, if sometimes it vanishes, you don't take that. Okay, it's understood. Okay, and this is the important thing is this is a colored directed graph. Okay. E alpha F alpha or EI Fi. Yes, it is defined only for simple roots alpha, and yeah, and there are finitely many simple roots. Even in the infinite dimensional case, that is, even if you are working over a Kac-Moody-Lie algebra, the number of roots, simple roots, is always finite. That's the, so it's alpha 1 through n or 0 through n, depending on how you index it. So this is a colored directed graph where if I have one eta belonging to this, and if I go by F alpha eta, so this is F alpha eta, then I point the arrow. So let me write eta prime here. So if eta prime is f alpha eta. Okay. Is this clear? That is how it's made into a directed graph, and the theorem just now says that B pi prime has a colored directed graph if they end at the same point. Right? Okay. So, as a corollary, so let's recall some of the corollaries that we did from this. Okay. Now, Ls of pi 1, right? So, suppose I take, let me write it out again. Suppose I take a path in this, and then I can conclude that I can talk about Ls of pi 1, right? So, pi 1 is a dominant integral weight, and therefore, I can talk about the Ls paths of shape pi 1, or that is, you take the straight line path and it is the B of that straight line path, right? Okay. That is in particular, so if I take pi prime to be the straight line path, then I see that this is, right? Okay. Right. Okay. And we know several things about Ls of pi 1, right? Okay. There is a unique path, for example, in Ls of pi 1 which is killed by, which vanishes under all E alphas, right, namely the straight line path itself. Okay. And therefore, you conclude that that path must be sent. So, the straight line path, so the conclusion then in particular pi 1, this is okay. Okay, or let me write the straight line path. Okay, let me not use that strange notation. The straight line path 2 pi 1 in Ls pi 1 is mapped to pi, because pi is a path which is, so pi is killed by all, because it is in the dominant wild chamber, because the image is in the dominant wild chamber, it is killed by all the E alphas. Therefore, it must be mapped to something that is killed by all the. So, is the logic clear? So, just from this isomorphism, I can also conclude that the straight line path is mapped to pi. Here is the argument. Pi belongs to pi plus, p plus, right? Therefore, every E alpha vanishes on pi. Therefore, when I map it to this side, and it's on a graph isomorphism, the image must have the same property, but there is a unique path with that image, with that property, namely the straight line path. Therefore, pi must go to the straight line path. Okay. Furthermore, so since there is a unique path here with that property, so pi is the unique path in B pi in particular. So, this, if you want, put stars here. So, this is one item, this is the next item, unique path in B pi on which all E alpha vanish. Right? Why is that? because there is a unique path here of that nature, there must be a single path. If is an isomorphism. So if there is a single path with that property here, there is obviously a single path with that property, namely pi. Okay, and also you conclude that every path in here. So since every path here is obtained from the straight line path by applying the f alphas, you conclude the same for this side. Is this clear? Okay. Okay, every element, every path in B pi is of the form f alpha 1, f alpha s, some string applied to pi. Okay, so those are easy conclusions. There was also a slightly more, not so straightforward, but nevertheless short argument to say that this the minimum value. So if I take any path in B pi, so here is another corollary which we proved yesterday. Corollary is for any eta, let's say in B pi, and for any simple alpha, the min of h eta alpha belongs to is an integer. Okay, and the argument for this, let's recall, the idea was to expand. Okay, so you suppose that the minimum is not an integer. So by contradiction, suppose it's not an integer, it will come, let's say it's minus 3.5. Okay, 0 is always it starts at 0. So if it's not an integer, means it has to be a negative non-integer integral value. Let's say it is negative 3.5. Okay, the idea is to expand everything by 2. Right? So 3.5 you write as 7 by 2, and then expand everything by 2, so that so on the one hand, eta is mapped to a Lakshmibai Seshadri path here, eta prime, and for that, for eta prime the value is the minimum. This property, the minimum is an integer, right? Okay, and if the minimum value is 3.5, then you know that E alpha maximum value you can apply E alpha is thrice. If you apply a fourth time, it's going to be 0, right? Okay. Now you know that for the Lakshmibai Seshadri path as well, right? That also will be, that is exactly 3 times, because this is 3 times, that is also 3 times. Okay, that's because it's a graph isomorphism, and because that is 3 times, its minimum value is minus 3. You know that, because for the Lakshmibai Seshadri path, it's exactly equal to the minimum value. Okay? Okay. Now you just scale everything, and what you conclude is that for twice this path, for twice the Lakshmibai Seshadri path, you will get the answer as 6, the maximum value of E alpha that you can apply, whereas on this side, it will be 7, which is a contradiction. Is this clear? And of course, you have to observe that when you scale things, when I scale things, here I go to 2 pi, be 2 pi. Here I go to 2 times pi over 1, and scaling preserves the, that is, if I take some isomorphism here, so let's write it out once again. So if I have this, there is Ls pi 1 B pi on the one hand, and then say B q pi, to use that notation, Ls q pi 1, and this is again, there is a CDG here, right? And there is a, on both sides there is a q. So eta prime goes to q eta prime. Eta goes to q eta here. Okay? Now, this diagram commutes. The reason being, because of the isomorphism, and when you scale the f alpha, instead of f alpha you put f alpha to the power q. Okay? So it continues to map things correctly, so this diagram commutes. This is another thing that you need to use in the proof of this. Okay? Yes, you will need that. It's a, yeah, you're using this as well. Correct. Yes. Is this clear? This is just a summary of what all we did yesterday. Okay. So this once again, this theorem is the most technically demanding, most important, most technically demanding theorem. Okay. So we will. I don't know how much of its proof we'll be able to do actually. We'll give it a try, good shot, next week. Okay. Today we will continue to derive some corollaries from it. Yes.
For the corollary, isn't it enough just that the endpoint is dominant and giving it pi and t plus?
Yes, very much. See, for example, yeah. So is the question clear? Is the question clear? Suppose, so question is, just because for the, sorry, once again, repeat the question, for the which corollary?
Yeah, no, actually the theorem itself we needed to read this. So I was thinking the corollary statement makes sense if the endpoint of pi is dominant.
No, that is not to be expected at all. That is not to be expected at all, because there are lots of paths whose endpoints are dominant. Okay, lots of paths whose endpoints are dominant. Right. So just because a path has, okay. So maybe let's just draw this picture. This has not been drawn. We have been drawing SL3 pictures. We have never drawn an SL2 picture. Okay. So let us draw an SL2 picture. Okay, to show why, right? So SL2 picture. Let's draw a picture of SL2. Okay, with the SL2 picture with the standard conventions, right? So you can identify H star with the real line. Okay. And the roots, the root lattice with the even integers, the weight lattice with the integers, with the, okay. And so this is the dominant Weil chamber, the positive, the non-negative part of the real line is the dominant Weil chamber. And so suppose so to say real number, so what are dominant integral weights? They are just non-negative integers. Okay. So suppose I take 3, for example, and take this straight line path. Okay. So let's, this is my pi. Let us compute. So pi is this. So pi of 1 is 3. So what is LS of pi 1? So I must keep acting E alphas, F alphas on it. So let's quickly do it. If I apply E alpha, I'm going to get 0. It's going to be positive. So if I act F alpha, what should I do? I must just take the least value, which is 0. So let me take alpha check, right? alpha check is just gives me on 1 it is 1, on 2 it is 2, etc. Okay. So, it starts at 0 and goes to 3. The graph looks exactly like that. So, I must reflect the part between 0 and 1. Okay. So, which means this part gets reflected the first time. So, let me draw it like this. This part gets reflected the first time, and after you reflect it, so maybe I'll, okay. So, and then the remaining gets added on here, right. So, this goes to -1, this goes up to -1 and comes back and joins here, right. Correct? Okay. What happens F2? Again, remember, I can just, instead of doing it twice, I can just apply it directly. So, which means I can reflect this one, right? So, if I do that, then I go here, right? This whole thing I've reflected. This is the extra bit. So, I come back here. And finally, I can apply 3 on this, the whole thing, right. So, it will go from 0 all the way to -3. Okay. So, how many Lakshmi LS paths are there? 4 paths. Okay. And they are precisely, if I draw 3, there is one ending at 3, one ending at 1, one ending at -1, one ending at -3. So, I can just use the endpoints as parameterizing the paths themselves, right. And what is the color directed graph? If I use red for, there is only one color, and that is the graph. Okay. So, anytime I take a path which ends at 3 and leaves and is contained entirely in the dominant wave chamber. So, I may go up to 2 and come back to 1, come down, whatever, or go this way, that way, and then come. So, I am not allowed to go this side and end at 3. If I take any such path as pi and look at the paths generated by that, there will exactly be 4 paths, right, and they will end exactly at 1 at 3, 1 at 1, 1 at -1, 1 at -3, and this will be the colored graph of that. Okay. Observe the following. So, let us do the same picture for 1 instead of 3. Let us take this path. No, they cannot be, because the endpoint is what? If I act f alpha on it, the endpoint reduces by alpha. So, if the original endpoints are the same, and if 2 things are mapped to each other, this is, suppose I get this by applying alpha 1 once, alpha 2 twice. I have decreased it by pi minus alpha 1 minus 2 alpha 2. So, the endpoint here will also be minus alpha 1 minus 2 alpha 2. Is that clear? Okay. Is that clear? Okay. Thanks, Shamik, for asking these questions. I am sure many other people have similar questions. Maybe they are afraid to ask. Okay. So, the endpoints. So let me state also the main the other main theorem. But before that, let me just do this. If I start with pi is this, just 1, then what is b pi? Just the other one, it just goes there's just one more path. You can apply f once. That's all f. There is only one, right? Okay. Now to answer your question, look here. There is this path ending at 1, and there is this path, the second path here, so maybe I should draw this more. The second path here starts here and goes like this and ends at 1. Okay? But this does not live in the dominant Weyl chamber entirely. Okay? So you could look at this path and this path. This has 4 elements generated by that, because this whole module is generated by that. This has 2 elements. Okay? So it's very important that not only is the endpoint dominant, but the path lives entirely in the dominant Weyl chamber. That's a very important. Okay? So in this, it is very important that that image is contained in DWC, the dominant Weyl chamber. Okay? Any other questions? So let's also state the, so what do you expect from these pictures? What is the character of the SL2 module with the highest weight 3? The other weights are 1, -1 and -3. The SL2 module with highest weight 1 is the defining representation, and its weights are 1 and -1. Okay? So this illustrates the following character formula. Okay? So let's write out the other thing. So that is another theorem which we are going to prove fully. So character formula. Yes, go ahead. I'm listening.
Yeah, here keeping track of the weights. How is it like in here everything is one dimensional the weight spaces? How is it keeping track of the multiplicities?
Because there will be several paths. We've already seen this in SL3 picture. In SL3 picture, for example, if you draw this, the one big picture, if you remember, that we have been drawing, there are 2 paths ending at 0. Okay? So there are 2 paths ending at 0. So the character formula is, right? Okay. Let pi be in P plus. Very important again that the image lies entirely in the dominant Weyl chamber. Okay? Character of B pi. Okay? So what do I mean by that? I have to define that, right? So let's first define this. Is sum over all e to the so I look at all endpoints, sum over those exponents. Okay? So of course, to make sense of this, you must ensure that there are only finitely many, given an endpoint, there are only finitely many paths ending there, because otherwise I'll keep adding. If I have a mu with many mu's, I mean infinitely many mu's ending at mu, paths ending at mu, then this is not, doesn't make sense. Okay? But here there are only finitely many paths ending at any weight, because every path is of this form, and once it is of this form, it is of the form pi 1 minus. So for if a path has to end at a point, that point must be of the form pi 1 minus sum of positive non-negative integral combination of the simple roots. Therefore, and if I'm given a certain mu and I'm able to, there are only so many ways I can use the various combinations of the mu alphas when each, various, the number of alphas is that I need to use is fixed, right? So if I want to get from lambda to mu, I have to use so many alphas, right? Okay. So the given number, but then you can put them in perhaps various orders, right? You could say instead of alpha 1, alpha 2, you could take alpha 2, alpha 1. There could be ever so many, these do not commute, remember? So there could be ever so many things which produce that. Some of them could be 0, right? Some of them could vanish, but point is there is only finitely many that are there. So this makes sense. Okay? The claim is that this is equal to the character of the irreducible module pi 1, exactly. Ah, thank you. Not good. Thank you. Right?
Actually, the argument that you gave gives the upper bound on the number of paths.
Number of paths ending at a certain point. There could be infinitely many paths, because in the Kac-Moody situation there could be infinitely many paths of a given. No? But if you're, is this clear? His question was, so this finiteness argument that we gave is for paths ending at a particular point, right? If you want to count all paths of a given which are in this B pi, right? There are finitely many of those if a G is a finite dimensional algebra. Okay, but if G is a affine algebra, for example, then it could well be infinite. Yes.
Not immediate, that if it's finite dimensional.
It is not. It is more or less immediate. It is more or less immediate. Let's see. Okay. Yeah. So at the moment I am not able to respond. So why is it? So the question is: suppose G is finite dimensional, then you want to say that can we see directly that this is a finite set? That's the question. Okay, maybe one of you can come up with an argument. Okay, at the moment I can't think of from its definition. Okay, so this is another thing which we are going to prove, and let me also mention this. This is the mother of all character formulas. Okay, in the sense that this will give you the tableau character formula, it will give you the pattern character formula, it will give you various character formula. Because it also gives you, let me also mention this, this is Littelmann, you can call this the path character formula. So let's call it PCF, the path character formula. Okay. So there is the Lakshmibai-Sheshadri character formula. So the Lakshmibai-Sheshadri character formula, which is almost the same as this, okay, is the special case of this when character of LS pi 1 is equal to, by definition, so LS lambda, let me write. Now lambda is a dominant weight. Okay. Now eta is in LS of lambda, e to the eta 1, this is character of V lambda. Okay, so this is a special case of this when I have put, instead of pi, I have put the straight line path. Okay, I have put the straight line path. But historically, this is the Lakshmibai-Sheshadri paths were defined by Lakshmibai-Sheshadri. So this is conjectured, although they didn't have the notion of paths. So remember, the Lakshmibai Seshadri paths were, there was another characterization given of Lakshmibai Seshadri paths, namely they have some integrality properties. They are, what was that? Rational paths with certain integrality properties. So that definition Lakshmibai Seshadri had. Okay, that definition they had, and they had conjectured by Lakshmibai Seshadri in it appears in the 1989 Hyderabad conference proceedings, which, by the way, this conference proceedings is a full of very nice papers. Conference proceedings. So they conjectured this formula, and then later on, for some 4 or 5 years later, Littelmann had this idea of interpreting those. So the path definition. So now we have now reversed the history in the sense that we are we started with the path definition and E alpha F alpha. Okay, that came later. Okay, so we started with that, and then he interpreted these the characterize. So he characterized or rather realized that the Lakshmibai Seshadri characterization of rational paths with integrality properties are precisely those paths that you get when you apply these F alphas to the straight line path. Okay? And then he also later on in the Annals paper proved the isomorphism theorem. This proof, okay, this conjecture is proved not in the, this itself is proved slightly earlier. So this proved Littelmann 1993 inventionist paper. Okay. So this character formula is really the Annals paper. So there, instead of this, there is a straight line path. You are taking any path in the dominant white chamber. Now, what do you get? It gives you a lot more room. You can take any path. So, for example, I could take that. Remember, for this 2 epsilon plus epsilon 2, I can take this path instead of the straight line path. I can go twice along epsilon and once along epsilon 2, or I could have done something else, as long as I am inside the dominant white chamber. But once I take that path, I get tableau. I can identify tableau as the paths that I get. This B pi can be identified as tableau, semi-standard Young tableau. Therefore, you will get the tableau character formula immediately. In fact, that's how we will justify the tableau character formula. Okay? Recall the tableau character formula. Since I am writing down character formulae, let me write down here. So for SL, so tableau character formula for SL and C. So if I take lambda is a dominant weight, then character of V lambda is given by I take all T semi-standard Young tableau of shape lambda and filled with 1 through n with entries this, and I take the weight of T. By weight of T, I mean just if you see 5 ones, then you write x1 to the 5 or t1 to the 5. If you see 3 ones, 2 twos and 5 threes, then you write x1 cubed or t1 cubed, t2 square, t3 to the 5, etc. So you will get you can generate a polynomial, and this, right? So this is the tableau character formula, and Ravinder indicated a way of proving this, which was you start with, okay, let's do it for GLN rather than SLN. So GLN to GLN minus 1, there is the restriction, and you prove that that restriction is multiplicity free, and then by that process coming from GLN all the way to GL1, or better still GL1 cross GL1 cross GL1, just restrict it to the diagonal diagonal elements. What you will get using that, you can actually prove this. Okay, that you may want to call that the Gelfand-Zeitlin way of proving it, because this multiplicity freeness of this GLN to GLN minus 1 restriction, and using that to exploiting that to generate, to get the character formula like this. Okay, they did it in terms of patterns rather than tableau, but just going between patterns and tableau is just, either, is just the same thing. Okay, so that is one way of doing it. And if you wish, as he was asking, if you want, that's a Lie algebraic way of doing it. He was asking if there are Lie algebraic proofs of the character formula rather than combinatorial proofs. So in a sense, maybe that you would call a more Lie algebraic, because you have proved a restriction theorem, observed something. Okay. We are now going to do a different way of doing it, right? How are we going to do it? We are going to prove this character formula for paths, and then say you can realize tableau as B pi when pi is chosen very specially. Okay, so, and of course you get this. So that's why I called it the mother of all character formulae, because it subsumes the Lakshmi-Bai-Seshadri character formula, the Gelfand-Zeitlin pattern character formula, tableau character formula, and generalizes them to all symmetrizable Kac-Moody Lie algebra, etc., etc. Okay, it's really a sweeping generalization. Okay, so that's okay. So we are going to prove this by Monday. At least we should have a proof of this character formula. Okay, modulo the isomorphism. There again, the isomorphism theorem is used. So modulo the isomorphism theorem. Okay, so let's see. Where were we? Can you please remind me where we had finished last time? What we had? Maybe we just got so far as the proving that the minimal was a okay. I think I have an idea where we finished. So before we can talk about the proof of the character formula, we need to know that there's, in the proof, there is another important aspect that is used, namely the action of the while group. On paths. Okay, and recall what this is. This is just paths ending at integral weights. The set of paths. In fact, you can, let's just cancel that. It acts on pi, I'll just define it on pi int. Okay? So what is the point here? So you see so let's call the while group W. So W acts on H star, right? By definition, it is realized as a group of, it's the group generated by the simple reflections, right, which all act on H star. So it's realized as a subgroup of GLH star. There is this weight lattice which is preserved by the action of W, right? So what does it do to an element if I take lambda in H star and if I act S alpha, what will happen? It will become lambda minus some lambda alpha check. So recall S alpha acting on lambda is lambda for any lambda in H star is just lambda alpha check alpha, right? This is the definition, right? And so if lambda belongs to P, this thing is an integer, right? So I'll get lambda minus a root, right? And if I act several times, I'll get, just keep subtracting some integrally many simple roots, either subtracting or adding, depending on, right? So if I start with an element and look at all the wild conjugates of it, they are all in the modulo, the root lattice, they are all the same. Therefore, P contains the root lattice, therefore this is preserved. Okay. So W preserves that, and W acts on P, right? And so what we want is the following. So there is this pi int to P. There is a map. What do I do with take an element here and just map it to pi 1, right? So want this to be W equivalent. So that is I'm stating a desiderata for the action even before we define it. If it's going to be useful at all, I would want the action. So this map should be such that, the action should be such that this map is a W map. There is an action of W here. If I'm going to define an action of W here, it makes sense for it to be such that this map is equivalent, W equivalent. Okay, so okay, so now that we have this picture, let me, yes. No, why is that obvious? I mean, you could define some stupid, for example, I could define the trivial action of W. It's a stupid thing, but I could define the trivial action of W, then it won't have this property, right? So, any natural action, any natural action of W, you would expect it to be W equivalent. Yeah, and it makes sense. Only then would it be useful. For example, we are going to use it in the character formula to reduce to the case, I will only have to do things for which are dominant, etc. Because then you can just push by W action, everything is, so you can reduce things. That's the way it's used. Okay, so let us draw this. Now that we have the SL2 picture, I've written this horizontally here, but let me draw this vertically. So you've worked with the usual is alpha string, right? So given a vector, then the alpha string to that vector. In Lie algebra representations, we always talk of such a thing. So you start with something, and you have the so let us do the alpha string now through a given path. Okay? So suppose I have a path here, and then I keep on applying the alpha string through that. So let me draw a picture here. It is kind of like this picture, except I'm now going to draw vertically. Okay. So pi is somewhere here, E alpha pi, so is not equal to 0. This p is maximal. This f alpha q pi is not equal to 0, q maximal. Okay. This is the alpha string through pi, right? So this picture is, I apply E alpha once. So F alpha you should think of as the inverse of E alpha, except that, with the caveat that F alpha could be 0 on something. Okay. So if I apply E alpha, I keep going up, and if I apply F alpha, I keep going down. Right? That's the picture, because the weight keeps decreasing by alpha or increasing by alpha. Right? That is exactly like the picture here, if you know SL2 representations. Okay? So how do I define naturally? So S alpha pi, I'm now defining the action of a simple reflection on a path pi. Okay? So let's say, so for simplicity, let's say q minus p is positive. Okay? That is, I can apply more times here than fewer times here, right? Okay. So then you set S alpha pi is equal to F alpha to the q minus p pi. Okay? Okay. So let us do this in this example and just check. Okay? Suppose I take this path, right, ending at 1. Okay? Look at the alpha string through this. So let's call this, I want to call this eta, right? Okay, let's draw this picture for that. Eta is the path that ends at 1. Okay? What is the F alpha string through it, please? So I keep applying F alpha or E alpha to it. If I apply E alpha to this, what do I get? So let me use eta 1, because there is a single path ending at 1. Let me just refer to the path as path ending at 1. If I apply E alpha to this, what happens? The straight line. Okay. I get eta 3. And what happens if I apply again? It vanishes. So, okay. Okay, and if I apply F alpha once, so I must reflect this, right? So I get eta minus 1. And then once again, eta minus 3. So what is, by this definition, what is S alpha of eta 1? So what are P and Q? P is 1 and Q is 2. So when I apply S alpha to this, it gives me eta minus 1, because I have to apply F alpha once. Okay? Okay? Okay. So that is natural, because I want this to lift. 1 goes to minus 1 under S alpha. So this is a very natural thing to be defining. Okay. There's another way of, okay. From this picture, this is one way of defining it. He gives an even simpler definition, although that is less transparent.
Eta 1 is that full going back and not the straight line.
Sorry.
I thought it's a straight path.
Which one?
Eta 1.
Eta 1 is not the straight path. The straight path does not even belong here. Does not even belong here. So one other thing to keep in mind, and we are going to use that, is in the finite dimensional case, if you start with a given some path, all other paths have the same length. So in the finite dimensional case, there is an inner product on H star. You can think of it as some real inner product space, right? And you are only acting reflections. These are orthogonal transformations. I mean, they preserve length. Okay? So if I start with a path of a given length, then all paths that I get by applying a E alpha F alpha to it, and so also now the S alpha or the while group to it, then they will all be of the same length. Is this clear? Okay. So if I have a straight line path going to 50, I cannot have a straight line path going to 48 in it. Okay. In order that it ends at 48, it must go some other direction and come back. Okay. Length as in the length of the, see, it's a straight line, it's a piecewise linear path, and you have an inner product. So it's like it's a piecewise linear path in Rn with a given inner product. Is that okay? Yeah. Okay. At this point, let me also draw one more example, which I think you should work with lots of examples. That's my suggestion. So another example to keep in mind is, so you've seen the adjoint representation, the paths for SL3 several times, right? Let's do the adjoint representation for the Lie algebra, which is not of type A, B2. Yes. So there are two questions. Okay, first Shamik, then Digjay.
Can we find the state of fixed point for this example? Is alpha acting on phi? What are the fixed points?
Yes, it's easy to find. You will get the answer in a minute. Just wait. Okay. Yes.
And we still check its action. We still have to check its.
Yes. That's the whole proof today. That's the whole proof. Yes.
If we just put S alpha pi is S alpha pi, will it?
That will just not work, because, for example, what is F alpha? So pi on this, it will take me from 3 to 1, whereas S alpha acting on 3 gives me -3. See, S alpha is the reflection in the origin. Okay, so is this question clear? I think it's an important question. Why can't I just take S alpha to be F alpha? That's the question. Okay. There are several problems with this. F alpha could be 0. Then what do you do? S alpha is a group action. Okay, it's an involution. It cannot, if on something non-zero, it has to be, I mean, it cannot take something to 0. Okay, it's a group action. Okay, so that is one objection. The other objection is it will never have this property, because, for example, if my path ends very far, like at 3, for example, then F alpha can only bring it to 1, whereas S alpha of 3 is -3. So it's kind of like, that's why this picture is good to keep in mind. So 0 is somewhere here. What you're doing is reflecting in that, S alpha is reflecting that thing in that string. See, it is just this reflection, except it's, so this is the point where no, that is a different reflection. No, I'm not saying that. No, I'm not saying that. This is not a path in that sense. This is just a schematic picture of.
The corresponding codes are where you draw the graph for the age.
Yeah.
There are some segments which
Yeah.
and have the corresponding portion in the graph.
Yeah.
S alpha only just reflect those portions.
You can think that way. You can think that way. Just, okay, maybe we'll come back to this question slightly, you know. So here is another way of, okay. So there is an equivalent definition. I'm giving you another definition. I'm not proving that the definition I'm giving now is equivalent to the definition given here. Okay, this is elementary. It's just very simple. So I expect you to do this. So here is the alternative definition. Okay, here it is. So it's, let's call. So he calls it S alpha tilde. Let me call it S alpha tilde. Okay. So S alpha tilde pi. Here is the definition. This is the definition given in the book, in the paper. F alpha to the n pi if n is, so you just look at the end point and act as many times, if that is positive, you act it F alpha so many times. If it is negative, you apply E alpha. It's as simple as that. This is the definition. Okay, that should answer Digjoy's question, because when is it fixed? When I don't do anything, right? When is it that I don't do anything? When pi 1 alpha check is 0. Then I don't do anything. That, okay? And to answer your question, so it is like if I am applying F alpha to the n alpha, that means I am applying n times F alpha, which means I illuminate it with a beam of light which is n in height, which column of light which is n from the minimum. I choose n steps, and that's the column and then I look at the illuminated portion, invert it. That's what I get. Okay, or if it is E alpha, then it's the other way, right? From the left, and so on. Okay, is the definition clear? Okay. Now I agree with you that we have to prove, and that's.
For the fixed point, the inner product is 0 with all alphas. So I mean, each alpha is a point.
No, that was what was his question for one given alpha, right? Given S alpha, that was his question. Okay. Then you are. Yeah, you could be 0 for all alphas. You could be 0 for all alphas if you are in the Kac-Moody situation without this being 0. Yeah. Correct? Have I said that correctly? Ah, correct. Stupid of me. Even here, if pi 1 can be 0 without pi being 0. Yes, very much. Yes. Yeah. But yeah. Of course, if pi 1 is 0, then it is fixed. The other thing is pi 1, even without pi 1 being 0 in the Kac-Moody situation, you could have alpha check is 0. Okay, all the alpha checkers. But never mind, you know, for a first pass, just think of the finite dimensional case. Okay, so let's do the. By the way, so one comment is that. What Digjoy was doing on Tableau yesterday is some version of this. So if you, in the tutorial, Digjoy was suggesting acting S alpha on semi-standard Young Tableau. He was giving some procedure and a while group action, right? And so the homework exercise is observe that, or prove or disprove that what he was giving is the same as this action. Okay? So if you interpret the Tableau as a path and take this definition, you get precisely what he was trying to do. Okay, that's the clear. Okay, let's prove. Proof. Okay, let's get to the so what do we have to do? So while group is defined, it's we know its generators and relations. These are the generators, and what are the relations? The square is 1, S alpha square is 1, and there are these braid relations. This is what we have to prove. Okay. Now S square is 1 is clear, right? That's easy. So have to S alpha tilde is an involution. That's obvious, okay, from the definition. I'm not checking it, it's easy. Okay. Now S alpha tilde satisfy the braid relations. Okay. This is where we have to do some work. Okay. So this is okay, and this is what we are trying to do now. Okay. The rest of today's talk will be why does S alpha tilde satisfy the braid relations. Okay. As preparation towards that, remember what we are proving. We are trying to prove that it satisfies the braid relations, and the idea is when do you have a braid relation, right? So this depends on that value of what does a braid relation mean? It is given two simple roots alpha and beta, then S alpha times S beta, whether it commutes or whether its third power is 1, or whether its fourth power is 1, or whether its sixth power is 1, or there is no relation. So these are the possibilities, remember, right? They commute, they second power, third power is 1, fourth power is 1, sixth power is 1, or there is no relation. Okay. So, and that depends on those values, that is alpha. If I choose alpha and beta, it depends on alpha beta check and beta alpha check. Okay. Yes. Yes, it depends on the specifically. No, this is the way to look at it. So when is there a braid relation? When alpha and beta are two simple roots with a particular. So for example, if you say if this is alpha check beta check and this is alpha beta, I am looking at that portion of the Cartan matrix, right? And I am looking at these entries here and here. Okay, what are the conditions? It's either both are 0 simultaneously. If one is 0, the other is 0, right? That's when they commute. That's when they commute. So you have to show S alpha tilde, S alpha. In this case, you have to show the commuting relation between these operations. I can say, what I am saying is, it reduces to the rank 2 situation. It reduces to the rank 2 situation. This is what I am saying. Okay, I am only worried about S alpha beta and S alpha. That I can just restrict it to that Lie algebra and just check. That's the whole point. And in fact, I can assume it is finite dimensional because otherwise there is no relation. Okay, so what we have to do is the following. Okay. So okay, just one comment. Okay, some of this, maybe some of you are not familiar with the Kac-Moody theory so much that these comments may not make much sense to you, but just think the following. The following is already non-trivial. Just assume we are in SLN. Okay, just assume we are in SLN. What are we trying to do here? S alphas you have defined. What you have to show is S alpha tilde 1 and S alpha tilde 2 satisfies the relation that S alpha tilde 1 times S alpha, no, I'll forget the tildes, just let me say it without the tilde. S1 S2 S1 is equal to S2 S1 S2. This is what you have to show. Okay, and similarly S2 S3 S2 is S3, for every pair of consecutive simple reflections, you have to show this. This is what you have to show. Okay? Okay. So, lemma. So, let G be finite dimensional and pi is in P plus. Then, for every W in W, so the G is finite dimensional, so W is finite dimensional, finite. There exists a unique path in B pi ending at W pi 1. Okay, let's prove this. This is a simple observation. Let's just prove this. How do you prove it? Is the statement clear? So, we are in the finite G is finite dimension. So, let's say we are in SL3. So, that means we are looking at a picture like this, right? And so, pi 1, pi is an entire, so this is the dominant wave chamber, and so pi is some path, let's say a straight line path that ends at some point here. Okay. Then there exists a unique path in B pi ending at, so all the way here. So, this is if W pi 1, this point, there is a unique path ending there. Okay, that is the claim. Okay. By the way, observe that this is never, these are never 0. Because given this, see if the endpoint is, so if I draw the H alpha for this, so it starts at 0, and since this is n, it goes up here, it ends at n, right? So, from the minimum to n is more than n, is at least n. Right. So, therefore, I can definitely apply F alpha n times. Okay. That is a simple observation. Okay. So, what is the proof of this? So, let me just write it. By isomorphism theorem, so, by isomorphism theorem, so whether I have B pi or whether I have B ls pi, ls of pi 1, it is the same. They are all the same. The endpoints are the same. So, by isomorphism theorem may assume pi is a straight line. Okay. Now, observe pi 1 or W pi 1 is as far from the origin, sorry for the vague thing is, but from the origin as pi 1, right? Because the distance between the origin and pi 1 is the same as the distance between origin and W pi 1, okay? And the length has to be preserved, right? So, you cannot have a path of length pi 1, or I mean this path has a certain length and every other path in B pi has the same length. So, you cannot get to W pi 1 except if you are a straight line. So, can get to, so all paths in B pi have the same length. So, cannot get to W pi 1 except by going straight to it, heading straight. Okay. So, I have expressed this differently. If you do not like this proof, you can you can, this is elementary and I leave it to you. Okay. But yeah. So, representation theoretically, Ravinder is suggesting, let us see what this says. This says that, so representation theoretically, you know that any, so this weight, this, take the representation with highest weight, this, that is one dimensional, and so are all Weil conjugates of that. Those are all weights of exactly dimension 1. Okay? Therefore, if you remember that, then you are not surprised by this. There is exactly a single path that ends at W pi 1. Exactly. So, if you, it's good to keep the thanks Ravinder, it's good to keep the representation theory in mind, and so you know what to expect. Of course, you can't do that, of course, you have to prove it from scratch, but at least you will know what to expect. Okay.
Just to comment later, in the example which we have done, that 0 was having multiplicity 2,
Huh.
but that is not a positive covenant. We have computed that.
No, see that is there, see that is you start with the straight line, in that example, to the other conjugates it was a straight line. Okay? Yeah. So, in general, the picture will be, see, the picture will be like this. All these things will be straight lines, right? There will be, right? And in between there will be lots of paths. Right? And the Weil group action which we are just going to prove means I can reflect along, it's a D3 or what is it, dihedral group of order 6, which is the same as S3 acting on this. So, you have that symmetry. Yeah. Okay, let us do the Braid relations. Okay, I'll erase this. So, we are trying to prove the Braid relations. Okay, proof of the Braid relations. So, may assume okay, so just for, let me write out the Braid relations. So, G is finite dimensional of rank 2. So, what is it? We have to show, let me explicitly write this down. So, I have chosen two simple roots, alpha and beta, with appropriate values of course, I have to also do this one. If G is of type A1 cross A1, S alpha beta, so this is S beta, S alpha, S beta. If G is of, so A1 sorry, S alpha, S beta, S alpha. So let me write it the way I have done it here. Okay. This is of type B2, and then S Okay. These are the Braid relations. We have to do this. It's okay. So, okay, may assume pi 1 is dominant. Okay, why may I assume pi 1 is dominant? That's a, suppose I want to check this and my pi is not dominant, right? I can just apply S. So if pi is not dominant, so let me do this briefly. It's a very simple thing. So I can maybe apply an S alpha to it, S alpha tilde to it. So instead of checking this on pi, it's enough to check this on S alpha tilde. You know, if it so happens that I have to check it on S alpha tilde pi, so be it. I check it on that. Okay. So see, these are involutions. Okay. So it follows that we may assume pi 1 is dominant. That is, I'm saying if pi is, maybe pi 1 is not dominant, but after applying alpha it becomes dominant. After applying S alpha it becomes dominant. So instead of checking it for pi, I reduce it to checking for S alpha tilde pi. Okay. And since, you know, when I apply S alpha tilde pi and check this, this side becomes, this side goes away, but then here I get an S alpha. Then I multiply by S alpha throughout to get what I want. Okay. Anyway, this is an elementary thing, so I leave it. Okay. So here is the interesting thing. We may assume further. So, pi 1 is regular. Okay. This is a very interesting checking. So let me try to show you how this is done. Huh? Regular means regular as a weight, which means neither alpha nor beta, alpha check is non-zero, not beta check is non-zero on that. That is it. For example, here, if it lies on this, one of these walls, it's called singular, okay, non-regular. Okay. So, for example, let's try to say we are here. Suppose I want to check that. Okay. And pi 1 is non-regular, say. How are we going to do that? So let's say pi 1, let's take an example. So let me take this to be H beta, okay, and this is H alpha. We are drawing the picture in, it's important that I draw this correctly. So this is 60-degree angle, right? And say it is not regular. So my pi 1 is here, right? So then So what happens when so I want to check S alpha tilde, S beta, S alpha tilde pi is equal, so this is what I'm checking. What about S? Same, right? So this is pi. Right? Okay. So let me see how to say this. Okay, let me. So let's add these S alpha, and so when I add S alpha, what happens to this? I go here, right? It's a reflection by this, right? And when I add beta, I come down here. So this is 60, this is, if I drawn this correctly, this is, it comes down here. Right? And so when I apply S alpha, so S alpha is beta is here. So just one second. S alpha is beta. Yeah. So and then when I apply S alpha to it, so see, this beta goes away. And what am I applying? S alpha beta, S alpha is beta. This is the same here. And then where do I end up with? I end up here, on which S alpha doesn't act. This you can remove this and you can remove this, in other words. So I'm just checking that equality. But that's trivial. Okay? So this is a nice calculation you can do. Okay? Similarly for weight 2, I mean B2, what you have to check is S alpha tilde S beta tilde S alpha S beta tilde pi. This is what I'm going to check is S beta tilde S alpha tilde S beta tilde S alpha tilde pi. This is what I'm going to check. Okay? So let's draw this picture again. So this B2, through two angles are 90 degrees. Okay? And so this is beta, and this is H beta, and this is H alpha. And let's say once again that I am here. Pi 1 is not regular, say let's say here. Okay? Which means this does not act. Okay? Which means when notice if this doesn't act, then these three are the same thing as these three. Okay? What I have to make sure is finally when I end up, this does not act. Okay? But where do I end up? Let us just do it. So if this does not act, alpha, I reflect by alpha here, then reflect by beta, right? So goes here, and reflect by alpha, goes here. Beta doesn't act. Okay? So, and I invite you to draw the picture for G2. That's also a very interesting picture. Okay? So, we may assume that it is regular. That's that's the upshot. Okay. Yeah, that's another, yeah. You could use that. You could use that, correct. So, if, here is the elementary thing. If I reflect in one plane and another plane, which is at angle theta to it, right. So, here is the statement, if I reflect in this line and another line, and they are two separated by theta, where measured from the first to the second, then reflecting along 1 and reflecting along 2, what is S1, S2? This is just rotation by angle 2 theta, where 2 theta should be interpreted, this being the direction. Yeah. So, this is a simple thing to keep in mind. Yeah. Though that may help you in doing this calculation, but I have just reflected them also directly. You can just reflect and see. Okay.
And the M is related, the length of the braid relation is also related to the angle.
Correct. The length of the braid relation is also related to the angle. So, here it is 90 degrees and it is 4. Here it is 120. I should get this right. Sorry, not 90 degrees. It's yeah, right, that's 45 degrees. The dominant while chamber has angle 45 degrees. Here it has 60 degrees, and the G2 case it has 30 degrees. That's if you draw the picture. Okay. Okay. Now let's so you are assuming that it is regular. Okay. Okay. May replace pi by m pi to assume so what is it? It's a piecewise linear path, right? So pi is some path which is ending in a dominant way, in a regular dominant weight, okay, but it's piecewise linear. So it ends at certain points, certain weights. By a suitable clearing of denominators, I can assume that it is a concatenation of straight line paths. Okay. So, of course, there may be some checking to do. If I replace it by m, then you're okay, etc. Okay. So, there is some, see, I'm going to check this on, not on pi, but on m pi. Okay. In fact, it's okay. So, why is this? So, why is this? Okay. So, here is the exercise homework. Observe S alpha m pi is m S alpha tilde pi. That's an exercise. It's a very simple exercise. You can use that, and so to say that instead of checking for pi, to say I want to check this equality when I put pi here, but it's enough to when I put m here. To check the two paths are equal, I can just expand both of them and check they are equal. And then I can move the m inside by that property. Okay? Therefore, I may assume that I can expand by m and assume that pi is pi 1. So, pi lambda 1, pi lambda 2, pi lambda r, where pi 1, where lambda 1, lambda 2, dot 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 lambda r are integral weights. And so, these are now straight line paths, landing and integral weights. So, what I am using about them is now that they are LS paths, right? And therefore, and so concatenation of LS paths. Okay? And a property of LS paths, remember, is that the minimum is an integer, right? The minimum of that H alpha is an integer. So, using that, so here is another exercise. So, let me state this theorem. Okay, maybe I'll, you know, okay. Suppose, so here is again a very elementary property of paths, but that is crucially used in this and several other proofs and applications. And so let me state that precisely. So, let me make a definition. A path pi in pi int, okay, did I write like this? Okay, has the, okay, and in the paper it is just called the integrality property. Since we have so many integrality properties already, I want to call it the minimal integrality property. Not a very good name, I am afraid, but just to distinguish. So, minimal integrality property okay, let's shorten it to MIP if minimum H pi alpha is an integer for every simple alpha. Okay. So, here is so let's assume that, so for such paths, for paths with minimal integrality property, the following is true. So, that is, let me write it. So, what I mean by this statement is that pi and eta satisfy the minimal integrality property. In this case, I am using the minimal integrality property with respect to alpha, but does not matter, we will state it. We will just assume that they satisfy the minimum, the MIP for all alpha and state it. So, it is one of these if m is less than pi 1 plus n, okay, otherwise. Okay. Yeah, what are m and n, right? Okay. So, m is equal to where? M is equal to minimum H alpha pi and n is equal to minimum H alpha, H pi alpha, H eta alpha. Okay. Okay. So, this is we will need to use this. So, let us just, this is a very important thing. So, let me just, so we are running out of time. So, I will maybe finish the proof next time using this, but let us, this is a very elementary thing. So, let us finish today by just doing an elementary exercise, namely the proof of this. Okay? This is just follows immediately from the definition of paths. okay? But it's a very important property. So let us just, I'll prove this and we'll finish with that. Okay. So let us draw the picture. Is the statement clear, first of all? Right? Okay. So I have pi, and m is the minimum. Okay. So let's say, so that is pi, this is m, and this is pi. This part is pi. And eta, so this is the transition, this is eta, and eta is something. So this is pi of 1, okay, and ends somewhere. So this is eta of 1, okay. This may not be a, let me see how I have drawn it. Okay, so maybe we'll just go up just for. Okay. Now, just from that picture, this should be clear. So so if I try to apply f on, let's just do the first one. Okay, the second one is similar. So let's say m is less than pi 1 plus n, right? So pi 1 plus n is this point. So this is, okay, let's say like this. Remember, n is the minimal, so this is n, right? Because it's the minimal for the second one. So pi 1 plus n is exactly this point. This distance is n, so this here is pi 1 plus n. You agree? That level on the y-axis. Okay. So if m is less than pi 1 plus n, so which means if m is below where I end at pi 1 and comes down by n. Right? If m is less than that, then my beam of light is going to go here. Right? If the m is less than that, then the beam of light is going to go here. Moreover, since this is an integer, this n is an integer, and they are all ending at integral points, pi 1, this thing where it ends, this thing is an integer, because this is an integer and n is an integer by assumption. Therefore, when I shine this light, if I take, see, remember I have to shine from here, right? And a beam of width 1. If I allow n to be a non-integer value, then n could come down. In which case, the illuminated parts will lie partly in pi and partly in eta. That should not be, right? So this is just the simple thing saying if they satisfy this minimal integrality property, then when you apply f alpha to a concatenation, then it goes in one or goes in another. It does not go, it behaves well. Similarly, E alpha. Okay, this is an important property. Okay, so next time there is a little more technicalities in the proof. So in case I am not confident of doing it on the board, I will put some portions of it into homework exercises, hopefully doable bits, and do that. And so finish definitely the proof of this next time, and then also proof of the character formula. That's what we may look forward to on Monday.